In this video, we're going to take a look at example 3 and another time of trying to understand if we can use the fundamental theorem of line integrals. All right, so I'm going to get us started here in terms of thinking about this. Let's suppose C is a smooth curve that starts at 1, 3 and ends at 2, 9. Again, I don't know what the curve is. I just kind of know loosely where it's located. So let's imagine 1, 3, 2, 9. I'm not even going to mark the actual or I'll mark on here the actual points that I'm working with. So we'll say that's up at 9 and this is over at 2, but I don't know how to connect those green things. They might connect with a line, they might not. And I want to suppose that the vector field I have is this gigantic mess. Can I find the exact value of this work integral? Oh gosh, all right. So again, it shouldn't be too terribly difficult to do because I know that since I'm only given the endpoints, I must be able to show that this vector field is conservative. Meaning, again, I can find a function whose gradient will equal this f. So that's what I'm going to hunt for. And that's what I'm going to ask you to hunt for. What would be something that I could select for the value of little f that could allow its gradient to turn into this? I'm going to give you a moment here to try to think about it. So pause the video and then hit play when you're ready to see the answer. Okay, so if you've spent some time thinking about this, you'll probably realize that it's really, really difficult to come up with some nice things that work here. One thing that might be interesting, though, is to think about these kind of one component at a time. And if you do that, you might be able to see that if you had something like e to the xy, that's always going to be remaining in your partial derivative. But here I might propose that maybe having a y in front would give me everything I need. And I'll let you go ahead and double check that. Okay. So I would say here then that the gradient of f is clearly going to be equal to my capital F of xy. So by the fundamental theorem of line integrals, we know that if I want to integrate across C, f dot dr, that's the exact same thing now as gradient f dot dr. And so now I know I can just go and evaluate f at my stop point, subtract what happens at the start point. And if you crunch this all the way out, I'll leave it to you to confirm, but I believe this is the value that I end up with. It's a messy number, but as always, ugly numbers are numbers too. In the next video, what we'll take a look at are some ways that we can begin to kind of expand upon the ideas that we're learning here and see some other cool connections between this fundamental theorem of line integrals and some other topics.